Today I want to talk about the detection of notches and cracks based on the monitoring of local strain and the solution of the inverse problem. My talk is divided into 5 parts. I will start with the motivation, then I will look at the distributed dislocation technique to solve the direct problem. Then I want to present some numerical and experimental verifications of our concept, and finally the summary. Briefly about the motivation, the picture left shows the demolition of the cabin roof due to material fatigue, and the second one describes the breakdown of the tanker with the crack roof. Therefore, it is important to detect and to monitor crack. So there are methods of crack monitoring. For example, methods are based on the principle of wave scattering of crack faces. This method gives information about size and location of the crack, but this method gives no information about loading parameters at the crack tip, and the measurement during operation is problematic. On the other hand, there are methods to measure the stress intensity factors, for example, by application of piezoelectric element or strain gauge, but this method is not suitable for crack. Therefore, our goal is the crack detection and parameter identification during operation of the structure based on the remote strain measured at arbitrary points. That means we can calculate the stress intensity factors K1 and K2, and we can calculate the crack lengths, the crack positions, and the crack inclinations, and the boundary loads. The approach to solve this problem is as follows. First, we formulate the direct problem, that is to determine a function which is dependent on the crack parameters and the boundary loads. The crack parameters are the crack length, the crack inclination, and the crack position. If these parameters are known, we can directly calculate the strain or the stress field. In the next step, we solve the inverse problem, that is that the strain at these points are known, but the crack parameters and the boundary load and the stress intensity factors are unknown. Now I come to the methods for the solution of the direct problem. The picture in the middle shows crack in structure or a submodel. To calculate the strain or the stress at arbitrary points, we have used 2 similar methods. The first one is the Poriforce method, and the second one is the dislocation technique. By the Poriforce method, the crack is replaced by distributed body forces, and by the dislocation technique, the crack is replaced by distributed dislocations. We continue with the dislocation technique to model, for example, a finite plate with 2 cracks. We assume an infinite plate with 6 cracks, and with corresponding rotation of 4 cracks, we get then our boundary, and the remaining 2 cracks are our actual crack. And then we cut out from the infinite plate, and we get then our finite plate with 2 internal cracks. So we can see that the boundaries and the cracks are simulated with distributed dislocations. So to calculate the strain at arbitrary points, we use the superposition principle of 2 solutions. The first solution is the solution of the stress due to dislocations distributed along the boundaries. And the second solution is the solution of the stress due to dislocations distributed along the crack. So the total stress is the sum of these 2 solutions. So the induced stresses due to one dislocation located at C is given with the system of equations. This column describes the induced stresses. Mu and kappa are elastic constant, and in this matrix are influence functions. The influence functions are known and can be fitted for various problems, for example, for the head plane. And this vector describes the Perkins vector, and the first component describes the dislocation in x direction, and the second one describes the dislocation in y direction. So we simulate our crack with many dislocations. Therefore, it is convenient to use the dislocation density. And the relationship between the Berger spectra and the dislocation density is given here. And now we can calculate our induced stresses at arbitrary points due to all dislocations with this integral equation. And here we have the dislocation density is unknown. So to determine the dislocation density, we use boundary conditions. The first is at the boundary, so that the induced stresses due to all dislocations at the boundaries is equal to the boundary load. And the second boundary condition is at the crack faces. At the crack faces is traction free, so the induced stresses due to all dislocations at the cracks is equal to 0. And we have here the normal and the shear stresses. So another boundary conditions are at the corner. So the dislocation density at the corner of the, for example, of the boundary A at this point is equal to the dislocation density at the same point of the boundary B. And it is the same here at this point and at this point and at this point. Another boundary condition is that the displacement jump at the crack tip is equal to 0, and we get then our integral equation. If we have a kinked crack, so the boundary conditions at the kink point are the same are to the corner, and we have also here that the displacement jump at the crack tip is equal to 0. And we get then our integral equations. These integral equations are singular integral equations containing Cauchy kernel. Therefore, it is convenient to use numerical solution. For example, Cauchy-Bichet quadrature. So first, we normalize the integral equation over the interval -1 and +1 by using the dimensionless coordinate S, J, and Pi. And then we write the dislocation density as two functions. The first function is a fundamental solution, and the second vector is the unknown vector. So the fundamental solution for the internal crack is given here. And we can see if Sj equal to -1 or +1, go then to the infinity, so at the crack tip. So, and then we will write our integral equation in the numerical equations, and we get then 1, 2, and 3 equations. And then we can write these equations in the matrix notation, and we get then our coefficient matrix, and we can calculate the known vector phi. If these vectors are calculated, we can calculate the stress field or the strain field. So in the direct problem, these parameters are known, so the crack length and the crack inclinations and the crack positions are known, but in the inverse problem, these parameters are unknown. So now I come to the results of the direct problem. We have here a finite plate with inclined crack. The plate size is given here. We have here crack position, crack length, and crack inclination, and the boundary loads. And we have calculated the strain field epsilon xx and epsilon yy with the dislocation method, and we have compared with the finite element method, and we can see that the result is similar. So we have also calculated the stress intensity factors for the curved crack. So the red line describes the kinked crack, and the black line describes the curved crack. So we have calculated the kinked crack with dislocation method and the curved crack with finite element method, and we have calculated the dimensionless F1 and F2, and we have compared with the dislocation method, finite element method, and we can see that the results is also in agreement. And the dimensionless F1 and F2 is given here. Now I come to the scheme for the identifying of crack parameters. First, we measure the strain with a strain gauge, or we calculate the strain with dislocation method or with the finite element method, and then we calculate or we solve the direct problem with the dislocation method, and then we solve the inverse problem with the genetic algorithm, and finally we get then our correct positions on correct length, correct inclination, boundary load, and the stress intensity factor. So I come to the numerical results for the inverse problem. We have here a finite plate with two inclined breaks. The unknown parameters are the boundary load, the correct inclination, and the correct length, and the correct positions. And we have here the given problem and the identified results, and we can see that the identified results of the given problem is similar. So the identified results emanate from the solution of the inverse problem, and the calculated strain here emanate from the calculated with these given parameters. So another example is the King track, and the unknown parameters are also here the boundary loads, the correct length, and the correct position, and the correct inclination. And we can see also that the given problem and the identified results is similar. So I come now to the sensitivity analysis of parameter identification dependent on number of strain gates. We have here three cases. In the first case, we have used 4 strain gates. In the second case, we have used 8 strain gates. And finally, we have used 12 strain gates. So this table shows the error between the given problem and trade results for 4 strain gates, 8 strain gates, and 12 strain gates. And we can see if we have small cracks, 4 strain gates are sufficient to determine the boundary loads of the correct parameters. If the crack is long, we need then 12 strain gates. Now I come to the experimental results. I start with the finite element method validation. We have here a finite plate with a notch. The geometry of the notch is given here. And we have calculated the strain component at this point with the finite element method. So I come to the experimental results. We have here a finite plate with a notch. And we have here the unknown parameters are the boundary load, the correct length, the correct inclination, and the correct position. And the given problem is here that we have calculated the strain for the notch with the finite element method, but the identified results emanate from the dislocation method for the finite plate with crack. And we can see also that the given problem and the identified result is similar. Another example is finite plate with 2 notches, and the unknown parameters are here the boundary load, the correct length, the correct inclination, and the correct positions, and another correct length for the other crack. And we can see also that the given problem and the identified results is in agreement. So I come now to the experimental results. We have used here a hydraulic testing machine. We have here a load cell, we have here a sample holder, and here is a sample with strain gates, and here is another cylinder. And we have here also the measuring amplifier for the strain gates. So we have here a plate made of aluminum with notch, and the notch is here, and we have here 12 strain gates. And each strain gauge measures 3 components of the strain. And the unknown parameters are the boundary load, and the correct length, and the inclination of the crack, and the position of the crack. And we have here the given problem and the identified results. And the given load here emanates from the, or is measured from the load cell. And we can see that the error between the given problem and the identified results is more than 10%. So, and now I come to the summary. The elastic field and the stress intensity factor for finite plate structure are calculated by using the distributed dislocation technique. And based on the data of measured surface strain, crack, and notches detection and parameter identification are obtained by solving the inverse problem. And in the future, we will do more experimental verifications of the concept and also for the curved cracks. Thank you for your attention.
Thank you.